Well, hello everyone. Welcome back to Zombieland Gaming. This is episode number 3 of Turing Complete. We are continuing our journey to build a computer within a computer. Maybe within a computer. Inception. Conception. That's not how I was trying to go with that. Anyway, today we are back again. This is hopefully going to close out all of the levels that I've already done prior to deciding that I wanted to do this. So then following this, we should be able to get back on track with actually doing these together. And I've already tried recording this once, and oh my god, did I go on a just offshoot and realize that I was struggling more than I needed to with some of these. So let's go ahead and get on in it. So in the past episodes, we did all this basic logic. We did these 4 memory portions, and then we did these bottom 3 of the arithmetic. So all we have today is these 7 in the arithmetic, and we are going to be starting with counting signals. So I am actually going to close out of this and go to my default schematic. Okay, so let's read this again. The output component of this level is a binary counter. But if you know anything about computers, it's not the kind of counter that you think. It's not counting up like a program counter where it's going from step 0, which is 0000, to step 1, which is 0001, to step 2, which is 0010. It's not trying to do that. It is literally trying to say, how many of these inputs are turned on? Is there 1 input on? Is there 2 inputs on? Is there 3 inputs on? Is there 4 inputs on? And then output out. So it's introducing a new little button over here that we'll discuss after I finish reading this. The first 3 pins correspond to 1, 2, and 4. So that's what it's talking about over here on the output. It's talking this right here. This top pin is 1, this middle pin is 2, and this middle pin is, the last pin is 4. So it'd be a 3-bit binary here. Use the binary counter to count the number of signals. The solution for this level is not very neat and requires more components. As you can see on the screen behind me, it took up the whole damn thing, right? So check this hint if you get stuck. This is what I did not pay attention to when I was designing this circuit. I completely went off on an offshoot, trying to get way too complicated with it. So let's check the hint. The circuitry for the ones bit is the same as what you did in the level odd number of signals. Copy and paste the odd number of signals. That's it, done. I did not do that. The circuitry for the 2's bit is what you did in Double Trouble, except when all 4s are on. So here's where things got complicated for me earlier when I tried to record this again. I actually tried to do this, as I recorded it, tried to figure this out. I didn't follow the Double Trouble part, though. I didn't pay attention to that. I was trying to use the Carnot maps and trying to figure all the circuitry out. Did not work properly. And as we'll see when I get into my second schematic, we'll see why it doesn't work. But essentially, we're going to utilize the basis of the Double Trouble level as our kind of how we're going to do it. So we're going to cover what I've done here on this screen, and then we're going to show my second schematic and then the final third schematic. So, okay, looking at this down below, this truth table, it's basically the same thing as all the other truth tables. It's just counting up in binary. We've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way through 15, right? When all 4 inputs are on, it's 15, as we have learned from the other episodes. So down below, though, you'll notice that we got like a number 4, and a number 3, and a number 2, and a number 1. They're kind of all over the place, and it doesn't look like binary. Well, that's because it's saying there's 2 signals. There's 3 signals in this one. There's 4 signals in the last one. And so the output over here is going to count in binary. So if the first one is on and the second one is on, that's going to be binary for 3. If all 3 of them are on, that would be binary for 7. So that's what we got to pay attention to, is we only want to have the top line on, or the middle line on, or the middle and top line on to get us 3, or just the bottom line. So that's something we have to make sure of. So my first thoughts on all of this is what I did was I don't have a spreadsheet or anything put up, but what I essentially did I sort my spreadsheet shorter will talk about this. So I basically spread it out. What is wanting just 1 signal? What is just wanting 2 signals? I don't care about 3 because 1 plus 2 makes 3, and then 4. So I took our truth table over here, and then I made an individual truth table for which ones need to suffice for 1 being on. So like in this case, right, this line right here, 2 signals. So I don't get 1 and 2, but I will in the 2 signal truth table, and I won't in the 4th, right? So I separated them out into the 3 individual bits. And then I did make Karnaugh maps for these portions. And all 3 of my versions of this, the first schematic that we're looking at is like the expanded out, didn't try to, I mean, if you look at this equation down here, A naught, B naught, C naught, and D naught, or A naught, B naught, C, D naught, or A naught, B, C naught, D naught, or A, B naught, C naught, D naught. I wanted to get that expression smaller, and the first time I did this, I said, forget about it. Let's just go ahead and make that table up. And that's the first schematic. And I did the same thing with the 2 signal and the 4 signal. The 4 signal is nice and easy because there's only one thing that turns us on. It's A and B, and C and D is the only thing that suffices for that. That's the most simplified you can get. It's A and B, and C and D, and those together. The 2s, however, is where things started to get messy and complicated because by itself, I did simplify this out using exclusive OR gates. I could do this much smaller. I mean, I've got papers all over the place with writings on it trying to simplify this out. But I used a property, one of the Boolean logic properties, which we haven't really talked about because they're hard to express here. I would definitely go look up Boolean expression simplifying, Boolean laws. There's a pretty handy table that you can find. Just search anywhere, Boolean expressions simplification, Boolean expression laws, or whatever, and you'll find a table with a few different laws on there, and they look very much like algebra. I mean, like if A and 0, then it's going to be 0. A or 1, it's going to be 1, and so on and so forth, right? So it does kind of look like algebra. Like if A or A, then you're going to get A. If it's A and A, you're going to get A. That kind of deal, right? So there's one that if you've got something knotted and something not knotted, ORed with something, like I've got it right down here, actually. So this right here, this little equation right here. A naught, B, or A, B naught. So the A's and the B's both swap in that equation. So that signifies an exclusive OR. Now, if you have A naught and B naught, or AB, then because the whole entire thing there on either side of that changes, then that signifies an exclusive NOR. But that's only for 2 inputs. So it gets kind of confusing when you start having 4 inputs, and that's where my brain didn't work. But I was able to shorten this down to A naught B and C exclusive OR D plus A B naught exclusive ORed with C D, and then A naught B naught C D, and then separated that out, ORed A, B, C naught, D naught. This is the part that I couldn't simplify. So I tried basically taking these 2 equations and making a schematic out of it. 1 worked by itself. 2 worked by itself. 1 and 2 together did not work. And as we're going to see, it's because I wasn't taking into consideration a 3rd signal coming in and basically turning off my 2s. In the case of this, it did actually work because I am actually worrying about the 3s here. I basically put the truth table into my my little schematic maker, and it just popped this out for me right here. So this takes into consideration both the 1s and the 2s. And then this down here is our 4 inputs turned on. So if we step through this, you're going to see how this works. So if we turn A on, right, or not, nothing's on right now. If we turn A on, it's look coming all the way through here. There's nothing coming through here, but hey, look, we've got not B and sorry, not A, not B. I've got this backwards, don't I? Oh yeah, okay. I've got this backwards. My orange line is A on this one. I change it up on the next. So we've got not D, not C, suffices to make this AND gate, but it doesn't go through anywhere. We've got A and not B makes this, not C, not D. So this suffices, right? Because we only have A turned on, the other 3 are turned off. So this suffices to make this AND gate, goes through this OR gate comes out to this OR gate, we get a 1 out. Coming over to the 2 section, nothing is being made here whatsoever because of all the, where the NOT gates and stuff are. These are basically 3 input AND gates, but just spread out to being individual gates. I could have just used a 3 AND gate here, and like you'll see on the last schematic. And then down here on the 4's number, we've only got an A input, so it's not making any of these AND gates. So now if we step it through to where one of the 2's are, So you can see up here on the 1, because of where I have all these NOT gates, it's forcing it to never look at a 2 input with another 2 input. But if we come down here to the 2 section, you can see we have A and B makes this AND gate, knotted with a NOT C, makes this AND gate, goes through an OR, and then also because we have A and B and then NOT D, because we want to make sure that we're looking at both C's and D's. So it suffices to make that OR gate as well, and it doesn't really matter which one of these makes it. It comes through to 2. Now, if we step forward to a 3, is going to be right here. You can see, where's it at? Right here. So we've got A, B, and C on, right? So if we come down to this line right here, we got A and B making this AND gate, C and NOT D making this AND gate, and it comes through. Coming down here on the 2s, we've got A and B and NOT D makes that, comes through. So we've got our 2 and our 1 makes 3. And if we step all the way through to the last one, the 4, oh god, let's just go all the way through like this. Yes, I understand. So see, we got all 4 turned on, so we make both these AND gates come out. So this works. This does work, but it is highly busy, highly messy. It took up the whole schematic. I wanted to make this smaller. So what I ended up doing was making a new schematic, and up here, what you're going to see is this is that equation from our spreadsheet. So if we bring up our spreadsheet here, you can see I've got A naught, B naught, so A naught and B naught, and the equation of C exclusive OR D, that whole thing ORed with C naught, D naught, and A exclusive OR B, right? So if we come back to here, what you can see is we've got A naught, and we're upside down now. I shifted. You can actually take these and you can hit spacebar and you can flip them around. So that's all I've done here to make this work. So now my A is on the right side and my D is on the left side. So we've got A naught and B naught is going into an AND gate. Then we've got C and D going to the exclusive OR. And then we've got C and D being ANDed, the NOT version, and then A and B being exclusive ORed. And then both of these just get ANDed together, and then whichever one of these make exclusive ORs out. So it works. So if I was to step through the first couple here, nothing turns on. Cool, nothing's coming out. See, I have my 4s is the same no matter what I do. But my 2s here works if I'm only just looking for 2 signal. If I'm not looking for 1 or 4 or 3, if I'm just solely looking for 2s, this works. And we're going to see that once I get to the 3. So if I push up to a 1 here, you can see I've got not C, not D, but I have A and not B. So that's going to exclusive OR out because I've only got 1 signal. This is ANDing with this one. We get an output. Cool beans. So if I come over to a first 2 signal, right, nothing in here is going to make because it doesn't suffice any individual component. Down here, we can see that we have not C, not D, but we have B and A, which is what we want. Cool. We get this AND gate. It comes out. It looks like it's working so far. So far, we've made all of our circuits. Look at this. Everything seems to be working just fine until we get to this point. And now we're showing nothing. And the reason being is because I didn't account for 3 signals coming into this circuitry down here and up here. I didn't account for 3 signals coming into any of these up here. So individually, this looks for 1, this looks for 2, and if we actually step it all the way through, look, it actually works on 4. So the only thing this is not working on is the 3s, unfortunately. So I had to go back to the drawing board. I mean, because, wow, look how small that would have been, right? That would have been really nice and nifty. So instead, I decided to go with this one. I decided to actually read the tips. Look, if we look at the tips, the circuitry for 1's bit is what you did in the odd number of signals. So if we zoom in here to these 2 exclusive OR, or these 3 exclusive ORs, let's go back to the level circuits here, and where is the odd number of signals? Look at this. Bam. That's all I did. I copied and pasted it, right? So let's come back into here. And then it says the circuitry for the 2's bit is what you did in Double Trouble, except when all 4s are on. So when all 4s are on, that's where you get your problem. So if we come up here to Double Trouble, we're going to see that it's a pretty simple schematic. So it's just A and B, A and C, A and D, B and C, B and D, C and D, and then they're all ORed together. Problem being is, once again, it's not taking into consideration 3 inputs being turned on at one time to get both the 1s and the 2s out. This is only going to output if there's 2. So as we can see, whenever there's 2 signals turned on, it basically, it's 2 or more, right? 2 or more. So it's always going to output a 2 pretty much all the time, and we don't want that. So what we ended up doing down here is, do I have another? I don't know if I schematiced it out. I don't think I did. Where did I get this from? My idea for this. How did I get my idea for this? Did I write it down? I had a whole thought process behind this, and I can't remember what made me do it. Oh. So, just my thought process behind it was, we just need to basically look out for the third number, right? So if we come to our spreadsheet, and let's just grab down here, right? So on our table, we're looking for 3 signals, right? So instead of it being just A B, A C, A D, B C, B D, and then C D, right? I'm just looking for 2 inputs. I have to worry about a third. So all I did was then I said C naught, and then D naught, and then we'll just say B naught, D naught. Actually, okay, this isn't a good example of this. No, cancel. I should probably write these out better. So I just started from the top. Now I want to worry about 3 inputs. So we go A, B, C naught. And we'll go A, B, D naught, because I'm not caring about C going into this gate. I'm just looking at just solely 3 inputs. And then we'll go AC, D naught, and then A. No, I don't really want to. Do I want to worry about A's again? AC. Oh, sorry, AC naught D, and then we'll go B, C. That's an S, D naught, and then B, C naught, D. What am I looking for here? A, B, C. How have I done these? A, B naught, C. Failing. Oh, yeah, A naught now, because I haven't done any A naughts yet. B, C, then A naught, B, D. That should cover it. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that should cover it. That should be all of them. So essentially, all I'm doing is I'm using the double trouble, but I'm just adding a third input there, and I'm looking for all of the possible combinations of 3. And the third one being, I don't want to see you. I want to see the opposite of you. So if you're turned on, please turn back off. That's all I've done there. So double trouble was looking at just solely 2 signals coming in, not caring if there's 1 or 3 or 4, just solely looking for 2. Whereas now we're solely looking for 3 and making sure the third one is turned off. So that was the thought process behind it. And that's what you can see here. We got A, and then, let me move this out of the camera's way a little bit. A, B, C naught. A, B, D naught. A, B naught, C. A, B naught, D. A, C, D naught. A, C naught, D. B, C, D naught. B, C naught, D. A, B, or A, C, D. B naught, C, D. There we go. So I've sufficed it now. Now I'm looking solely for 2 signals and canceling out the chance that there's a third, which means this one will catch our 1s. We'll have our 1 plus 2, and then the 4s remain the same. So if I actually go ahead and turn this on, we'll actually be able to see this. So nothing turned on, nothing comes out. 1 turns on, you can see it suffices this exclusive OR, goes to this exclusive OR because it also suffices, come down. And we can just skip the 1s, go to a 2. Now you can see that this exclusive OR up here has 2 inputs going into it, so it doesn't turn on. C and D's not even turn on, so it doesn't care. So 1s aren't even bother now. But we've got A and B coming into this AND gate, along with a C naught, and then we have A, B, and D naught coming in here, so it suffices to make that, boom, we got our way coming down. So that is a 2 working, cool beans. And then let's go to the 3. So now here's where all my trouble was with the 3s. So because I'm looking specifically for 3, we've got, right here, A, B, D naught makes this, because we don't have D turned on, and hell, you'll even see it down here. We've got A, C, and D naught turns that one on, and then we have B, C, and D naught turned on. So all 3 of these AND gates are going to the OR gates putting out. So there's because there's three combinations there of two signals, right? But then we also still have, because we have A and B coming in here, turns this exclusive OR off, but we only have C out of the C and D, so it turns this one on. So we get our 1 plus 2 makes 3. Yes, we're finally cooking with steam. Hopefully this makes sense. And then with the 4, it's just the same as before. All of them are turned on, we get an output out. And you'll notice, because I'm looking for 3 signals on all of this to output a 2-signal code, because all of them have all the signal turned off, all these inverters basically swap, so I don't get any of these AND gates sufficing, and then we have 2 signals going to each exclusive OR, so we don't have any 1s. And then we just got the 4s bit. Yay! Done! Dusted! Holy crap, that was a ginormous mess, let me tell you what. Way more of a mess. And that covers all of that. And so now on to the next one. That was a longer explanation than it probably needed to be, but hopefully you guys understood. It required a pretty good size explanation. All right, half adders. So now we're finally really starting to build some computer components. We measure the universe with numbers, so your machine must learn to count. Treat the inputs as on or off, off or on, 0 or 1. 0 being off, 1 being on. See, this is one of those things they should have explained a long time ago. This is the first time that they're explaining 0 is off and 1 is on, depending if they are off or on. Add them together in binary such that the result is either 0 or 1. As with normal addition, if the result cannot be described with 1 digit, set the carry to 1. So basically it's saying, I only have 0s and 1s. So if I want the number 2, I can't put that there because I only have an option of 0, 1. So what you'll end up doing, because we have everything to the power of, 2 to the power of n, you'll go a 0, cool, I'll put a 0 out. If I got 1 input, put a 1 out. If I have a 2 1s, then put a 0 and send the other one to the next higher bit because it's going to be 2, and so on and so forth. So what you're going to see here is, you can look this up online. If you type in half adder schematic, half adder circuit, half adder, it'll bring up this exact schematic. It is the schematic for it. So if you look at our truth table, if we have input turned off, then we get nothing out. If we have 1 on, we get 1 out. If we have the other one on by itself, we get 1 out. If we have both on, we get 0 out, but then we have the carryover because that's going up to the next, if you want to attach it to another adder or use that carry for some other function. So all we're doing here is we're looking exclusively for 1. If not, you're going to look at 2. Because if you got no inputs coming in here, nothing's going to happen here. But if you have both inputs on, it's going to AND those together and allow this AND put to go out to the carry. So it's a very simple circuit. So we'll step through it real fast. See, we got number 1 is on, doesn't turn the AND gate on, so we have no carry, but it turns the exclusive OR on, and we get a 1 out. If I step it over to the B side, B, exclusive OR is out, but it doesn't turn on the AND gate, so we get no carry. If we have both A and B, which makes 2, then we get nothing out of our exclusive OR, but we get our AND gate turned on, and we get our carry out. So that is a half adder. It's a really simple circuit. And all right, so next level, so that is half adders. And then let me see, what do we got next? Double the number. All right, so I have good news for you. The large gray creature with huge ears and a trunk that was favored to win was disqualified on a technicality. Good job for disqualifying the elephant. He doesn't need to be here anyway. He was seemingly startled by this tiny rodent creature and ran, eventually puncturing the ship and causing quite a stir in the canteen. Did they play the music? Please, that's the cantina, but similar thing. The input and output of this level are using bytes of bits. So they're introducing another new component in here. So most computers have bus work, right? So instead of having just one line taking everything you need, because that would have to send a signal, send the next signal, send the next signal, and keep sending signals one after the other to eventually be collected to then make whatever you're trying to make. Instead, we can use these bits and send multiple signals all at one time on a bus work and then bring them out to whatever component we need. And that way we can send a lot of signals, get a lot of signals over where we want them, and then decompile those signals to whatever function we're trying to do. So bits are one individual line. Bytes are, in this case, it'd be 8 bits makes up a byte. So that'd be 1 through 128. The input and output of this level, blah, blah, blah. We already said that. Okay, the input and output of this level are using bytes instead of bits. One of these, the 2 new components you were given, takes a byte and splits it into the bits, and the other does the opposite. So you really don't have this in real life. I mean, you would use components that do this functionality, and the way you would draw it on schematic symbols, you could just put a little, squiggly wiggly thing, and then just put like 8, 16, 32, whatever your number of bus lines are, 4, whatever. Using these components, figure out how to double the input number up to 127. If you're not familiar with binary, you'll have to experiment. So once again, they're not even telling you what binary are. Even though we already did a binary racer where we had to add the numbers together in binary to get the number out, they haven't really explained what binary is, really, right? Zeros and ones. Right side of the schematic will be the least significant bit, 1. And then 2, 4, 8, 16, 32, 64, 128, 256, 5, 12, 1024, so on and so forth. As you add more bits, leftmost side will be your most significant bit, generally. So, one thing to note, if you're struggling with this, it's because it's kind of like one of the other tests where you can't change the schematic after you've started. So you have to kind of fumble through it until you realize you just need to build the whole schematic all at one time. And then no matter what number they throw at you, you will be doubling it. So that's what we have here. So essentially all I've done is I've just doubled it by taking the input line, which we have over here, byte splitter. So that's taking 1 byte in and then splitting it out to the 8. And then the byte, what a byte maker is what they're calling this. And that's basically then taking all those individual bits back out to 1. So what we're seeing on here is the whole byte. So all I've done here is I've connected the input to the doubled output. So 1 goes to 2, 2 to 4, 4 to 8, 8 to 16, so on and so forth. And then no matter what number they give me on the input, it will get doubled. So if we play our test, you can see first number, 1 times 2 equals 2. Hey, look, I've got 1 times 2 makes 2. 33 times 2, so 33 is 1 plus 32. Gets me 66. Boom, I got 66 coming out. Look at that. It actually flows on the output. And then you can also see our truth table up here. So this is showing what inputs are on. It's basically 1, 2, 3, 4, 5, 6, 7, 8 across. So from right to left, next line down, right to left. So we've got the 2-bit on, and then we've got the 32-bit on down here. So that's going to be 35, 34. Jesus, I can't math. 34 multiplying up to 68. So I'm just going to step this all through because you kind of get the picture, right? So, 121 is going to be 64, 32, 16, 8 plus 1 makes the 121 doubled 242. You kind of get the picture there. But that was the frustrating part, is they didn't explain that, one, you're going to have the whole schematic made before the end of the test, or you're going to keep failing it every single time. They don't change the numbers up. It's the same numbers every single time, though, so that's good. So just as long as you have all the lines connected, you're good to go. All right, onwards. Okay, so next one. So we've done counting signals, we've done half adder, we've done double the number, and now let's move on to full adder. So just like an adder, right? All we're doing in this case is that now we've got an extra bit coming in, and so we're going to add, instead of just 0 and 1 making 0, 1, or 2, now we're going to have 0 plus 1 makes 2, plus another 1 makes 4. And so we're going to have to basically take a half adder, add it in with another adder. That's all we're doing. We're taking 2 adders together, and the output of the carry from the first adder is going to connect to the input of our next adder, and then the carry of that will be our actual overall carry out. So that way, if you carry out on that second adder, it's going to turn into an 8, because our first adder turned into a 2, second adder, turns into a 4, because it's going to be 0, 1, 2, 3, and 4 will be our carry. There you go. Sorry about that. So in the previous level, we added together 2 inputs. This time we add 3. Once again, add the inputs together in binary such that the result is either a 0 or a 1. As with normal addition, if the result cannot be described 1 digit, set the carry to 1. So ignore this for a second. If we look down at our truth table, basically, as we have 1, we're going to get an output. If we have 2, we're going to get a carry. So in this case, input 3 is turned, the only one turned on. We'll have an output, but no carry. If we have 2 outputs here, which means 2 inputs here, which means you're going to get a carry. 2 inputs here, which means you're going to get a carry. 3 inputs here, which means both of these are going to carry. Our first carry, however, is going to, we're going to get the sum and the carry, because we're going to get one of them actually outputting out, as we'll see, and then the other one's just going to be the extra. So it'll be, 2 plus 2, essentially. So all I've done here is you've got this, and this is our first adder. And then this plus this is our second adder right here. And then I'm just ORing these ands together to get our carry out. I don't know why I decided to do that. I really didn't need to do that. So if we got nothing turned on, we've got nothing going on. If we turn just the A input on, we're sufficing to make this exclusive OR gate, which is sufficing to make this, which means we get our sum, but neither one of the AND gates. And if you notice, I have the first adder is the first two inputs here are going to our AND gate. The second input actually goes up into this exclusive OR, and this is kind of hard to see because of this line right here. Let me see if I can grab. Can I not grab this, please? Like this. Not. Hello? Why can I not select you? Move, please. That's coming off of here. There we go. You know what? Let's just delete line right here. Line right here. And let's walk. There we go. All right. Now you can kind of see that a little better. So yeah. So basically our input is coming into our exclusive OR of the second adder. The output of our first adder, which would have been our sum on the last, the half adder, is going into the exclusive OR now. So we're taking the addition of this plus the addition of the third input, and then we're just taking these two lines coming down to our next carry. And so essentially I'm just getting a carry over here. I don't know why I decided to do it this way, but there we go. So we see our 1, so let's go ahead and step back through. So now if we have the B input on, we do the same thing as what we did with A, and now our first time we're going to get a carry. So, oh, I know why I did the OR. Normally I wouldn't have put this OR here. The carry, the carry would be used for something different. So we basically have A and B turned on, so it suffices this AND gate going through the OR. We get a carry out because they want to see the carry here. I had to show that there was a carry instead of just, letting it go to the next adder like we're going to see in the next lesson. But because these don't make the exclusive OR, we get no exclusive OR out here. So our sum is essentially the carry, which would be 2 binary. If we turn the third input on, we get our carry out because it suffices to make this exclusive OR over here, but we get no carry because the AND doesn't turn on. Now, if we come up to here, which is going to be binary for 5, we suffice to make this exclusive OR because only the A input is on, but because this is coming in here, we do not turn this exclusive OR on, and we get our AND gate out here, and, sorry, 4. Be 1, 2, and 4. Yeah, so that'd be binary 5. That is not how this works. This is how it works for their truth table. I should have a sum. Yeah. I'm doing it based on their truth table. Because this would be a 1 giving us a sum plus 4, which would give us a carryover because that has to go to the next bit. Make 5. All right. And then we've got 2 plus 3, 4 plus 2, which makes 6, carrying over again, because once again, we're not going to get a sum here. They're wanting to show that you're having to carry over to another adder. And if we turn all of them on, we're going to get a sum and a carryover because now we're sufficing to not make this exclusive OR gate, which means only this one's coming in, making the sum, and then we're ANDing these together and actually getting a carryover out. So not quite how a full adder actually works. I had to do this to base it off of their truth table to get the carryover out, which is this portion right here. Normally this wouldn't be how this would work, but it suffices to make their truth table. That's the main point, is making sure that we got the truth table. So we've got a half adder with this OR gate combining the two carryovers to get our carry out that they wanted to see. All right, so that suffices that, and now we're on to Byte OR. So these last ones are going to be pretty simplistic. You may think it is unethical to put down all of you animals that don't win the competition, but you would be wrong. Since all these animals lived in the wild, we assume they lived good lives. Also, we consume their meat afterwards. That makes it okay somehow. Good grief. Or together on each bit of the byte inputs. When I first did this, I struggled a little bit because I was like, what are you trying to get me to do? Literally all they want is 1 or this 1, 2 or this 2, 4 or this 4. Like if I come in here, let me do some coloration here. 1, change our color. 2. Oh, no, not that one. Oh. Green, yellow, hello, yellow. Hello, can I please click on this? Thank you. Darker shade blue on this one right here. Okay, you can kind of see the picture, right? Let's just go with gray on this one just to get it there. There you go. All right, so now you can see. That's all I did. I literally took 1 OR to 1, 2 OR to 2, 4 OR to 4, and then made an output. That is exclusively it. See? There we go. So, don't worry about the number that's coming out. It doesn't really matter. It's just wanting to show that there's an output based on this truth table. So if 1 is indicating the number for 96 and 2 is indicating for the number 103, it's either or. Bam. So see, they're wanting to get 103 out, so ORed 103 comes out. That's all that's showing. Just ORing all the inputs together. Like. And then this one, this one, Byte NOT. Same exact thing. Our previous model of brain size being the main predictors of intelligence was naive. Dr. Raku's new models show tool making and usage is key in the early evolutionary stages of developing intelligence. Good to know, guy. Therefore, the number of arms on a creature is clearly the main predictor of intelligence. Did you know there are sea creatures from your planet with 4 times as many arms as you and they are doing better in tests? Octopuses are pretty smart. Not eat bitch at the byte input. Literally, that's it. Take the input, byte it, or not it, send it out. Not it, send it out. So we'll just run the test, and bam, you can see that no matter what, as long as I was nodding, like in the case of this, 79, it wants to see the opposite of 79 in binary. Put a not on everything. That's all that level wanted. So basically just kind of showing you that you can inverse a byte, which sometimes is handy for if you're addressing versus going to a program counter. If you want to save space, you could have your program counter be a different address than your register address could be a different than your RAM address or something like that. And you could just simply use the inverse of it in order to get the same same amount of information. All right, adding bytes. So here we go. So this one's going to be a little bit different. Add the 2 input bytes. Each output bit in the output should be a result of the addition of the corresponding bits from the inputs and potentially a carry. That sounds like a mouthful. So they give us a new piece here, and that's this full adder. Just like with the SR latch, they don't tell us what's what on this thing. They've just thrown it at us and said, here, you figure out what this hell thing this is. So, because I played around with it, this right here, let me zoom in a bit. The top button here is going to be your carry in. So, from a different adder coming out, the carryover from a different adder can go into here. Or the sum could go into here if that's what you wanted to use it for. Or if you just wanted a totally on signal, like in the case of this, I normally wouldn't have plugged this input in, but in the truth table they give us, at one point they turn this on, so you have to have it connected. And then the middle one is input 1, the bottom one is input 2, and then the top line on the right side is your sum out, the bottom one is your carry out. So all I've done down here is exactly what we did with the ORing, is we've got 1 and 1, adding them together. And then in the case potentially that we have an input here, a carry in, that would be, a 3-bit adder, a full adder with that 3rd bit. And then we have our sum coming out down here to what the sum would be. In this case, so 1. And then we've got our carry out going into the carry in of the next one down. So they're just cascades. So the carry out of the 1st bit goes to the carry of the 2, carry in of the 2. The carry out of the 2 goes to the carry in of the 4. Carry out of the 4 goes to the carry in of the 8, so on and so forth, all the way down. And so we're just going to count in binary. So it's adding the 2 numbers. So what it's going to do for us is, once again, you have to have the whole schematic built before you start it, because it's going to throw numbers in and it wants to make sure it adds it properly, which is why you have to make sure that this input is in here. So if I step it in, you'll see our truth table is asking for 255 plus 255, which means all of these bits are on. Technically, you've got 256, but 0 doesn't count. So 255 would be your number. And then it says it doesn't have the carry in turned on. So as we can see, the carry in is turned off. So it's not worrying about it. And then our output needs to be 254 with a carry. So there we go. We got it. Once again, it's going to add 81 plus 1. Or sorry, this is bit 1. So 1 and 81. And we're going to get 82 coming out. And we do. So on and so forth the entire way through. So that's all it's doing. This adder, and it looks like, now that I'm looking at down here, 249 is the bottom one. So technically this is input 1 and this is input 2, which is backwards from every other lesson that we've done. The top one has always been input 1 on every other lesson, which is why I hooked it up the way I did. But obviously, this adder really doesn't, no adder really cares about what's input 1 or input 2. You have to know which one you're using as input 1 and 2, because you can put whichever input to whichever input. You just have to, if you've got an input 1 and an output 1, you want to make sure that the input and outputs are the ones that you want to use. So in the case of this, it doesn't really matter because we're only having the one output coming out. So no matter which direction the input 1 and 2 are, our carry is going to be the same. Now, if I had taken this, sum line and put it on the carry out and put the carry out on the sum line, then of course we would have had everything completely wrong. But those for sure are exactly what they are. And that pretty much covers everything we've done so far. So I know this is long episodes with a lot of stuff coming at you really fast. But I wanted to really get through all of this, just so that way now we can get into doing just an episode, which will make the episodes much shorter. And there's so much information that it's hard to pack a lot of information in such a small episode, which is why these episodes are going to be really long, because there's a lot to do to understand how these things function and work. And I'm sure I'm still scratching my head with my own explanation. So if you need any further explanation or need me to revise how I said something, definitely leave a comment down below. If you want to see me explain something in a little more detail or pinpoint you to some information on the internet that might explain it a whole lot better than I did, definitely comment down below. This is mainly a game, right? It's a game. It's for fun. We just want to see if we can achieve making a computer with inside a computer and be the ultimate geeks and nerds. But at the same time, I'm hoping that you guys are learning some stuff as well, because all of this is the basis for how the big giant thing that's right over here, it's how that is working. It's this is, how your Xbox works, how your CD player works, how your phone works, all that stuff, how your Xbox controller works. It's all based off of this stuff. So it's cool to learn exactly what makes this thing. And all this stuff goes back to the 60s, 70s, and 80s. This is the very basic components of building any computer. You can actually end up building this in Minecraft, for crying out loud, with redstone logic. So anyway, I hope you guys enjoyed. I know it was a long one. I really appreciate those that stuck around. Once again, I'll put timestamps in the episode. I did revise the very first episode. I put the timestamps in the description. So that way, you can pinpoint which spot in the game. If you're having troubles, you can go straight to that section. But yeah, so this is going to be coming out on a Saturday, and that means following this will be a Wednesday Satisfactory episode, unless I get some gumption to do another game. So thank you very much, everyone. Don't forget to like, subscribe, comment, share with the universe, and I'll see you guys in the next episode. For now, bye!